Okay, so now we're going to start talking about how to exploit sparsity. What I mean by sparsity is the data is high dimensional, but there are low dimensional structures we can exploit. Structures in it that we can exploit, right? So we'll talk about several approaches to that. One of them is just a standard sort of approach called principal component analysis. The other one is compressive sensing, and then layering additional techniques on top of these dimensionality reduction techniques. But before getting into these techniques, I first want to make the case that if you didn't have sparsity, you can't really do much, hope to do much. And so I'm going to talk about what is often called the curse of dimensionality, which is actually, you'll see, a rather obvious observation. What it means is that if we allow the data and our objective to be too general, so we have classification or regression objectives. If you allow the data and the objectives, that combination, to be too general, then the number of training samples for learning anything scales exponentially with the dimension. And you'll see that it's actually a very simple calculation to see why that would be the case. So let's start with a regression problem to show what can happen there. So what's the regression problem? I have maybe training data as usual in d dimensions. I have real valued labels, and I want to learn a map y equals fx. This is what I want to learn. And of course, I need to make some assumptions about the function f to enable learning. Basically, if the function can be completely arbitrary for different values of x which are close to each other, learning cannot happen. So let's assume the minimum that we can. So intuitively, the minimal assumption we can make is, let me first write it in words. So if x and x prime are close, then fx and fx prime are close, right? And one way to guarantee it is, for example, via some sort of Lipschitz condition, which says that the difference, the magnitude of the difference between fx and fx prime is less than or equal to some constant L times some norm difference between x and x prime, right? And this norm can be a 2 norm or an infinity norm. For simplicity of argument, for now, I'm going to put it as the infinity norm. So the difference between the maximum components of x and x prime. And this idea of Lipschitz property is the reason why this constant is called Lipschitz constant, right? So suppose we have that. What does it mean? It means that, suppose, let me just do a 2D example. So suppose my data lives in a box of size 1 by 1, and you give me some point x here, then I could, draw a box around it of, say, size 2 epsilon, because in any direction the difference in the coordinate cannot be more than epsilon. So I can draw a box around it, and I can say that within this box, whatever x prime I choose, fx prime minus fx is less than or equal to L times epsilon, right? And so for a given Lipschitz constant and a given level of approximation that I want, I can figure out how big these boxes have to be. I can think of it in another way. If I don't want to center around an x, again take that box and build these epsilon squares that tile it, right? Size epsilon, and between the furthest corners of these boxes, the L infinity norm difference cannot be more than epsilon, and so these guys all will be the functions here will be within L epsilon of each other. So it's a pretty minimal assumption on this function, and if I wanted to just say, okay, I want to, give enough, training point such that I learn the function to within this. I could do it by tiling this space of size 1 by 1 using squares of length epsilon on each side, and the volume of each square is the area of each square is epsilon squared, and the box area is 1. So if you give me one training point per box anywhere at all in the box, then for any new data example that falls in here, you will be able to just predict the value of the function there to within this approximation L times epsilon, right? So this many training points is good enough so that wherever you are, wherever you throw down a new data point on which you want to do an inference, there will be a box there with a training point there, such that you have a good enough approximation for the function here at this cross point, right? At this x prime point. You denote that by star. Of course, the problem is when you go to d dimensions, and now you say, well, I have basically a d-dimensional box of side epsilon, and you sort of grid using d-dimensional hypercubes. And suppose your space is still of side 1 on each dimension, so your volume of the data space is this hypercube of side 1, so it's 1 to the d, which is 1, and I'm gridding using these little boxes of if I have size epsilon hypercube, the dimension is the volume is epsilon to the d, and now you see how things blow up, right? Basically, your number of hypercubes that you need of this size is of course 1 over epsilon to the power of d. Epsilon is of course smaller than 1, and this is of course exponential, right? So basically it's exponential of log of 1 over epsilon times d. So it grows exponentially in d, and I think we have made a reasonable assumption about the function. It is smooth enough that if I am close enough to the if I have a training point that is close enough to a new point on which I have to do inference, I can get a good estimate of the function. That's a very general and generic assumption on the function. You would say now, what if the L infinity norm is not the right thing to talk about? Well, that's pretty easy as well. If you put the Lipschitz condition in terms of the L2 norm, like fx minus fx prime, magnitude is less than or equal to some other L, there's a different L, times x minus x prime, L2 norm, and suppose we are talking about data lives in d-dimensional unit sphere, just completely analogously, and basically I'm going to say that basically I'm going to tile, I guess, or cover the unit sphere with spheres of radius epsilon. Well, you always have, it's the same, exact same argument as before. You have, in d dimension, you have some constant, k sub d, times radius to the power of d is the volume of a sphere of radius r in d dimensions, right? So, I know what, k sub d is, what is it? It's pi r square, right? So it's pi for d equals 2, k sub d is 4 over 3 pi for d equals 3. But basically, it is some constant that depends on d. So again, you have exactly the same argument as before. So the number of, spheres needed to cover the data space, and for each sphere, you must have a training point to give a good enough approximation. So it is going to be k sub d times 1 to the d divided by k sub d times epsilon to the d, which is 1 over epsilon to the d, and still exponentially blows up. So under generic assumptions on the function, it's we will need an amount of training that blows up exponentially with the dimension. So exactly the same argument applies to classification as well. Basically, in classification, you are trying to map a point x, to a function fx that takes a discrete set of values. Whether you want to think of one-hot encoding or just enumerating the classes, say 1 through k, it's a function, and you need to know that basically this function doesn't, this function cannot be completely arbitrary. It has to have some properties that if I'm close enough, then my class is likely to be the same, right? In this context, I should mention that there's a very interesting result many years ago, Cover and Hart, 1967. They showed actually that the nearest neighbor rule, so for example, let me just phrase it in the context of our notation. So I have these n training points that are given to you with labels y1 through yn, and now I have a new point x star on which we want to do inference, and let me define the nearest neighbor as the nearest training point according to some metrics. So it's the minimum I between n and 1 of some distance measure. It could be L2 norm, it could be something else, some more general metric between x star and the training point. So that's the nearest neighbor, and we will say that f of x star is going to be exactly the label I was given for the nearest neighbor, right? So this is my one nearest neighbor rule. You can also have a k nearest neighbor rule, basically, where you take some consensus among the k closest point, but asymptotically it doesn't. The one nearest neighbor scheme is pretty much the best according to Kober and Hart. So this is the one nearest neighbor rule, or nearest neighbor rule for short. And the key result of Kober and Hart is that the probability of error for the nearest neighbor rule is less than or equal to 2 times the probability of error for the map rule that actually knows all the distributions. And then this part, let me change pen color, this is sort of the limit of the probability of error, limit as the number of training point gets large. And well, so how large? How large should these training points get? And it turns out that in the proof of these results, the basic entity that comes in there is that what they show is the reason all this works is because as n gets large, the nearest point comes close enough to the inference point. So the proof shows that as n gets large, xi star essentially tends to this x star in some sense. And when I say tends to, it means comes within a small distance of, right? And that's where your curse of dimensionality again comes in, because if I am relying on this to make things happen, and this and when I look at the sort of the volume over which I'm working, that volume is really shrinking exponentially. So here again the epsilon to the power of d is the volume. Or let's say I'm talking about Euclidean norm. K sub d times epsilon to the power of d is the volume of the small sphere that I'm talking about. And if that's what you need for the classification to work well, again you are back to the curse of dimensionality, saying that covering the entire space needs n to grow exponentially with the dimension. And so that's what the curse of dimensionality is. This curse, of course, appears in many situations. It appears to optimization. So if I'm optimizing an arbitrary function, and I say I'm going to grid the space small enough so that I don't expect much variation. Again, you have the same thing. Your volume of those of the hypercubes or spheres is small compared to the overall data space, and the ratio is growing exponentially with the dimension. So that's where the curse comes from. So given that, pretty much to succeed with a number of data points that does not blow up, I need some sparsity. So this supplies the motivation for saying, actually, if empirically I'm succeeding in my inference task with a reasonable number of data points, that means it cannot really be as general a function as the ones for which we see the curse of dimensionality. It must be a simpler function that I'm trying to learn. There must be some low-dimensional structure in there that I'm learning. Whether it's linear, nonlinear, I don't care, but there must be some low-dimensional structure that I'm learning, and that's what I am calling the concept of sparsity. And we'll just see a few examples of how to apply it algorithmically.